So in part B, we have this tank Y now, which has an open top open to the air, and we're told it is connected to a short horizontal pipe of radius r, which is a height h0 above the surface of the water level. And we're told that the top of the water level is moving downwards with a constant speed of Vs. And we're told at time t is equal to 0, the valve is opened. We need to derive a relationship between the exiting speed as a function of the surface's speed in part 1. So what we need to use here is the Bernoulli equation. So we know that P1 plus the potential energy plus the kinetic energy will have to be constant. However, what we can say is that the pressure will have to be the same in both points. So what we can say is that 1/2 for the top surface, then we have 1/2 times the density times the surface speed squared plus its potential energy. So the density multiplied with g times h. And then this will be equal to the density times g, and then the height of this we assume to be 0. So we take this height as to be 0, and then we add 1/2 times density of the exiting speed squared, Vp squared. And then we can simply see that Vp squared is equal to Vs squared plus 2gh. We can cancel out, we can divide with the densities, we can multiply with the 2. So then we will see that Vp is equal to the square root of Vs squared plus 2gh. And then in part 2, we're asked to derive the relationship between Vp and the changing radius r of the top surface of water to show that this relationship holds. So what we need to remember here is the continuity equation, which is that the volumetric flow rate remains constant throughout the entire system. Therefore, we can say A1 times V1, so the surface area over here multiplied with the speed will have to be the same as A2 times V2. And well, the first surface area is pi big R squared times Vs. Second surface area is pi times small r squared times Vp. We can rearrange this for Vp to find that this is r squared over small r squared times Vs. And then in part 3, we're told that when the radius r of the tank is sufficiently greater than r, the speed Vp can be approximated with this. We justify this claim. So what we can say is that when an r is a lot bigger than small r, then from this formula we can see that Vp will be much larger than Vs, like this. And what we can see then is that in this formula, if Vs is so small, then we can simply approximate the speed of the water the surface of the water to be 0. So we can say this is approximately 0. Therefore, this term simply falls out. So we will find that Vp is simply equal to root 2gh.